Hi and welcome to another Hopper tutorial video. Hopper is a modern semicolon and curly brace language, much like Java or C#, but without classes, and it's intentionally, the architecture is such that it's easy to port it and run it on small devices like 8-bit microcontrollers and 8-bit CPUs and microcontrollers. This is the basic structure of a Hopper program. In C, this would have main in front of it, for example. In Hopper, it doesn't need it. In this tutorial, I'm going to walk through what the options here do, the compiler options. So this compiler options tutorial, I'm starting with the last one, which is save on build. So if I try to build right now, which is the F7 shortcut key, so if I build, it's going to offer me save. So if I wanted to not be prompted on every build to save my changes, I can just check save on build. So now when I add another method here, and I'm going to call my method. This program doesn't do very much yet. I need a semicolon after that. Now, in the top right, we can see that the file name, the path for this file is orange, which means it's not saved. But since I have save on build, when I press F7, it's going to save it and then build it. Right, so at the bottom of the screen here, we can see success. It compiled test.hs, which is Hopper source, and it output test.hexe, which is Hopper executable. And the Hopper executable is in the bin folder. So unlike Visual Studio, which by default outputs your created files, the ones that you don't check into version control, all under your project, Hopper doesn't. Hopper puts them somewhere else in your tree so that it's easy to get rid of them. So let me first go and show you how that works. So in the Hopper console, let's go back to the root. So if we go dir, how does this work? So you can just say, what are the dir options? Okay, so dir, let's look for test.star, and let's look recursively. See what we get. Okay, so there's a test, the hexe, which is what we compiled into the bin folder. There's under bin, there's an options folder with test.options, and that's actually where we store these options. They're stored per project, and the project is named based on the name of the primary file in the project, and the primary file in the project is the one that's got the word program in it. So test.options is also stored under bin. So that's what this one is. Then under the debug folder, there's test.hasm. So that's where it output at the end of the compilation step. Actually, I don't have it set. That's from a previous build. I didn't have run disassembler, so that's old. So if I looked at the timestamps, that would be older than this. Well, older than my source. But this is where it'll output your disassembly, so that you have disassembly to look at. We'll look at that later. And under debug/obj is where it's putting intermediate code. So it's like the obj files under Visual Studio, Visual Studio with C++, for example, makes obj files. And then our source code is under source, testing, source. There's something called test. So another way to look at this is to do full paths, and then you'll see it more clearly. So the exe is in the bin folder. The options file is under the bin folder. And then under debug, it's got all these temporary intermediate files, and there's the source. And the benefit of this approach is that you can very easily delete all your intermediate files without worrying that you're going to delete your source, or you can easily make a rule in your GitHub repo to say ignore this entire subfolder, and then they won't appear when you make changes. So all the bins go in there, and it's an easy way for the shell to find them as well. So it looks first in the current directory for an exe if you try to run it. So if I try and run test right now, it'll just do nothing because the program does nothing, but it found it under the bin folder. So first it looked in the current folder, and then it went and looked in the bin folder to run test. All right, so that's our first option covered. That was save on bill. Run disassembler I've already mentioned. So if you watch the bottom of the screen, there's the last step probably. No, it's sort of flashed there that it's very quick. So it made a new version of the disassembly, and we can easily look at that. Let's switch back. So we can easily look at the disassembly. We've got a utility called show, and I can go debug test.dasm and -n for more. Oh, didn't like that. Oh, didn't find. What did I do wrong? Oh, yes, DASM would be a different platform. HASM, right. So this is the syntax highlighted output of compiling that source code. So we can see we've got two methods. So we've got this method and this method. So the main calls method. So let's go and have a look at our disassembly. Main is always, in the binary, is always method 0. It enters it, test main. It names it main, even though it's anonymous in the code. It's the entry point of the program, is to start at this address, hex A, which is hex A there. Enter creates a stack frame, and then there's only one instruction in main, which is to call, and it does it by method index, call method 1. This is the method table up here. So method 1 starts at hex F. So it's calling test method, and there's hex F, and what does method 1 do? Nothing. And it just returns, and then this returns, and we're done with our program. So program doesn't do very much, but here's your assembler. So let's switch back, and so that's this disassembler input output here, which is useful for trying to. It's useful if you're trying to look for a system error. Usually you won't need to look at it with your program, if you're just writing Hopper programs and never really caring about how they get translated or compiled. Next option, I'm not going to talk about generate ihex because I'll just briefly mention that we convert a .hexe file into a binary format that we can transfer across the serial port. So this is to transfer it across to 8-bit microcontrollers, or to 8-bit CPUs or microcontrollers like the Raspberry Pi Pico, where you need to generate ihex. Extended code segment is also something that you don't really need to care about. It was a way of squeezing a little bit more space out of the limited 64K address space. And there's only right now 2 programs in the platform that require it. They're the biggest programs. It's the Hopper compiler itself and the Hopper debugger are quite big. So you don't need to know about that one. Run optimizer. Exactly what it sounds like. So let's see what happens if we run the optimizer for this program. And we've generated a new, let's see what our new version of the hexe looks like. The HASM looks like. It's a bit shorter now. So it doesn't do very much. So it realized that the method was small enough to inline, so it inlined method the call to the method, and the inline to the method is nothing, so it enters and exits, it does nothing. So the optimized code is a little smaller. It's also a little harder to debug. If you have a real program and you run the optimizer, sometimes it's easier to debug the non-optimized code, but if you're trying to debug at a system level. So we'll leave optimize off for now. And then we have something called create checked build. I call it check build because that's what Microsoft Windows used to call it back in the days of Windows 3 and Windows NT. So you could have a whole build of Windows that was a check build, and it would insert extra code into your executable to do checks at runtime. So after doing a check build, it's injected. Let's do that again here. It's injected some extra instructions into the executable. So specifically this test BP on exiting each function. And what that's doing is checking that all the stack use within this assembly is correct. You want to exit your method with sort of a balanced stack frame. So that's an example of something that's inserted by the check build. Now we'll go into something that's more relevant to someone who's actually just writing a Hopper program rather than trying to debug the platform. And I think I'm going to make a second method, just so that you'll see why later, so it makes it more clear when we have a stack trace. And we have method 2 here. Now I'm going to create an integer I equals -1. And now I'm going to cast that integer to a uint, right? So clearly that's, well, let's do it first with a 1. So that's perfectly fine. So if I run this program, let's run it from the console so we can see what happens. We run test, nothing happens. We can make it more interesting. We can do a print then well, let's do UI to hex string, four significant digits. So okay, there we go. So we're going to print out the output of that, and if I try to compile this, it's going to tell me it doesn't know what 2hex string is. Yep. So at the bottom of the screen there we see it doesn't know what 2hex string is. So I can make that more obvious. Let's make it like that. And that's because I haven't included any users clauses to include any system APIs. So there's one, made a mistake. So it's under source. All of this is under the source tree in the repo. So if we double click on that, we can see system includes a lot of other things. So I'm looking for uint 2hex string, which is in the uint here. So try parse hex, try parse. There, 2hex string, that's what we were looking for. And then I can double click on the main program to go back. So now if I compile it, it's not going to know what print is. There we go. So if I double click on this error message, it'll take me to the error. And there it is. So we're missing print, and that's because that's it's a device, so it's not included. System is mostly language features. Screen is we want one for print. Now we compile, and we have a success message at the bottom of the screen. Let's flip to the other screen. Now if we run test, we get hex 0001. Which is what we expected, because we just made it 1. I can show you what the HASM looks like again. Let's just clear the screen. And there we go. And now it's prompting for more because it's gotten a little longer. So here's all our code in the test method 2. And it's pretty verbose because it's not optimized. But yeah, it's doing a cast here. And I should turn that off. So let me do it without the checked build and show you what it looks like. So if I do that again, right, let's go down. So we're in method 2 here. So the part of interest here without doing a check build is casting the int to a uint. So it makes a slot on the stack by pushing a 0. It pushes this local variable, which is I, onto the stack, and then cast to 4. And 4 is the uint type, and then pop it into the local variable slot it's made, which is this uint slot here. And you might think that binary they're equivalent, but the cast, there's actually a place on the stack for a type. So the runtime type in Hopper, the runtime stack in Hopper is typed, and that's why it needs a cast. It needs to change the slot on the stack from one type to another. And if I don't have a checked build, and now I'll do something like make that -1. So that's now outside the range of uints because it's less than 0. But I'm not running a check build. So if I just run it here, we get hex FFFF, which is the binary equivalent of -1 for a signed 16-bit integer, but it doesn't mean anything. It's, it's the largest possible value for an unsigned integer value. So, 65,000 and something. So clearly that's a programming error now. So if we switch on create checked build, and then we rebuild, and now we run test again, it gives us a runtime error. And it's a meaningful runtime error. It's telling us the cast failed, error 8, cast failed, and it gives us a call stack. And this is why we need those intermediate files. So to try and find out what went wrong, I've got a utility called red screen of death. This is our red screen of death. So RSOD and the name of the hexe. It'll find it by itself, and it'll give me a decorated call stack. So the same call stack we just saw above, same error message, but it'll give me some source references as to where the error was. So it's telling me the top of the call stack is where the failure was, so it's line 9. So line 9 is this, and it's got the source code line there as well, there, and it's showing where it was called from. It was called from line 15 in method, it was called from here. Method 2 was called from line 14. It's actually the return address line, which is the line after that. So it's actually the brace after the call. And the same is true of line 19 in main, is that. Anyway, so checked build, let's see what it did in the... Well, let's first go and have a look at where this information came from. So if we go to the debug folder, and then we go to the obj folder, and we do a dir test.star. These two files, test code and test JSON, is where the data came from. So if we go more test.json, not more, I always do that. It's like, yeah, other platform. So show test.json with the dash more for more. There you go. So this is the this file was created by the preprocessor. That's got like where the global elements exist. So where the start of test main is, where the start of test method is, all that sort of thing. Which units were included. So test main starts at position 259, or screen print is in system screen. And it starts at position 1168 on line 49 in screen, so it tells you where all the stuff is. So that's the one kind of useful debug info. Let me get through all this. Yeah, it included a lot of units, so it's going to take a while. There we go, we're through it. And then if I do, let's show the other one is smaller. This is because the preprocessor doesn't know which code was used and which wasn't. So that was the entire system. So if we look at JSON.code, code is the output. So the preprocessor generates JSON. The compiler consumes that JSON and generates code, and then the optimizer consumes code and generates the same file code. Let's have a look at it. This is the code. It's a lot smaller. But it's actually the binary code of each method. So method 0 is the main method, and that's the instructions. There's only 7 of them, and that includes the operands. And then it's got these are the line numbers and the offsets. So that's the offset into the code. So byte number 1, 0, 1, and byte number 4 is 0, 1, 2, 3, 4. Those are the instructions, and then this is the corresponding line number in this source file. And line 17 is where the method starts, and then the same for the other two methods that we've defined. In addition, it's also got these ranges here which tell the debugger when certain local variables are alive for between what range and what range. So this information is used by the debugger, and it is used by this utility to give you a decent stack trace for that error that happened. And the way it remembers this is when there is one of these failures, it creates a crash.log somewhere. It only keeps one at a time. So this is reading the last crash from crash.log, which you can go find. I think it is in the, it might also be in the debug folder. Can't remember right now. Anyway, that is how the check build will find you runtime errors. If you turn it off, it'll assume you're happy that your code is stable and running, and you don't need the speed penalty of checking the range. I can show you what it looks like too. So where's it going to be? Debug test.hasm-more. Yeah, so let's go have a look at what it looks like. So in the checked build, instead of just casting to 4, I don't know if you can remember, you might have to wind back to see. All it did last in the non-checked build is it pushed the 0, pushed the value, then called cast to 4, and then called pop. So it was 4 instructions. In the check build, it inserted the code in between. So it duplicated the top of the stack, pushed a 15 hexf, bit shift to the right. So it shifted the copy to the right by 15 bits, which means that the most significant bit of the either uint or int is now in slot 0, bit 0. And if it's a 1, it means that it's got a sign. If it's, because this is an int, negative, so that most significant bit is a sign. So then it says if it's 0, it means it's within the range, so it's in the positive range, so it's okay to cast it to a uint. So if it's 0, jump if 0 forward by 4, so plus 1, 2, 3, 4. So it would get to the cast instruction because the program count is currently there, so plus 1, plus 2, plus 3, plus 4 gets you to cast. If not, it calls die 08. And die is a opcode to say generate an error, fail at runtime. I think there's a way to figure out what these mean. The names of the errors, strings for them. Maybe not in runtime. Huh. Yeah, they're somewhere in the source so that you can see a list of what all these numbers mean. But they get spelled out during the expression, during the crash as well. It tells you what it is. Okay, let's do one more example. So let's just make that into a reasonable number. And let's make it into a big number. And then we can go I divided equals 4. Let's compile that. And let's clear the screen and test. Well, that didn't work as well as I was hoping. Cast failed. Oh, that's an old error message. Because I should have looked at the bottom of the screen here. It didn't compile because I was still doing uint to hex string. Whereas I should just, actually we can just print to string here. We don't need that. So let's just do that. And success at the bottom of the screen, and now let's try running it again. So 25 is our output. Not showing you that, let's fade back. So yeah, 25. My previous run was of the previous bad build. So yeah, 100 divided by 4, 25. Okay. So do we have a check build? Actually, it doesn't really matter if you have a check build or not. This will fail both times. So if we divide this by 0, what's going to happen? Let's build that. And then let's run it. Yeah, division by 0, and then I can do a red screen of death test, and it shows us the line on which the division by 0 error was. And I think it'll happen even if you don't have a check build, because it's still going to be a division by 0. So we turned off the check build, we built again, and run again. Yeah, same thing. Different. You can see the stack addresses are different because it's not the check build anymore, so it's smaller code. But yeah, it's division. Obviously there's errors that get caught when you're not in a check build as well, like a division by 0, kind of hard to miss. Other things that will crash like this is like out of range. So if you try and read beyond the end of a string, or if you try and use an index into a collection that doesn't exist, either a dictionary, a list, or an array, and you can use the check build. Well, it won't really help you. It's still going to crash this way. And that's using this under your program, right? Which seems reasonable because you built your program, and therefore the content of the obj directory included the output from your program, these two lines. But it actually includes a lot more, and that's because on my machine I've built the tools as well. So if I look at, I have the debug info for the compiler, for example. And this is a young system. There's only me working on the system right now. So obviously it's pretty stable, but it still has its issues and some bugs, and it can crash. So if you get one of those, if you run something in the compiler and you get an unexpected red screen of death in the compiler, if you try and run RSOD to say where is that in the stack trace, you're not going to be able to see, because you're not going to have the debug info for the compiler. So there is a way to get it easily. So if I show tools.cmd, so CMD is an extension for batch scripts, command line batch scripts, like batch files. And this tools.cmd runs a sequence of command line instructions to build all the tool chains in the compiler tool chain. So the disassembler, the optimizer, code generator, preprocessor, and the compiler. So if you can build from source, this is how you build the tool chain from source. And if you did that on your machine, then you'd have more useful debug info that you could share with me if you had a crash. And there's another one called sys.cmd, which builds all the other tools that, so if one of these crashes on you, you could build these tools. And so that's show, which is the one we're looking at right now. The shell itself, which is where the cursor is over here. The directory command. There's a terminal program that connects to a serial port that you can use for connecting to a device that when you need to do a serial terminal. Port is a way to select ports for, like, if you've got two different microcontrollers connected at the same time and you want to switch between them. HM is the hopper monitor, which is like a assembler level debugger to connect to remote devices like 8-bit CPU devices or microcontrollers. So it's a hopper virtual machine level debugger. Debug is the symbolic debugger for debugging on microcontrollers or 8-bit microcontrollers, so the one that's in the user interface that you call from the IDE. RSOD, red screen of death, that's the thing to dump a decent stack trace. But you need to have debug info to be able to do that. Edit is the editor. Okay, I think I've covered, optimizer. Makes your program a lot smaller. So let's have a look at what that looks like. So let's do that. And if I do, you can do all this at the command line as well. So let's go to cd source testing. So if I'm in the folder and I say preprocess is the first step in the toolchain, preprocess test, it knows I'm in .hs. I could type .hs, but it knows I'm in the current directory. So preprocessor runs. So it successfully ran the preprocessor and generated the intermediate JSON file. Then if I say compile test, by default it'll go and look in the obj folder for the JSON file. And if I do -o, that means optimized. So in addition to not doing the runtime checks, it would also do peephole optimization. So let's not do that. And then I could just do code gen, which takes, so this generated the test.code file. And then if I generate that, I end up with a binary file. So completely non-optimized with all the runtime checks. This little program, which does very little, just a single division and a print, is 218 bytes of code. Now, we don't have to pre-process again, but if we compile again with test.o, it should, and then we do code gen. Okay, we went down from 218 bytes to 175 bytes, because this is now without the checked build checks, and it does peephole optimization in the compiler, so minimal optimization that happens at compile time. And then there's a optimizer for program level optimization, whole program optimization, and that should have a little bit more of an effect. Let's see. And yeah, so it took it down. It tells us there on the screen, and then we do code gen. So we went down again from 175 down to 142. So there's a significant difference between a completely unoptimized program and a maximally optimized program. And that difference is significant if your program's big. So if you have a program that's 20K of code, for example, there's a significant difference between or 21K and 14K, a significant difference. And of course, the best instruction is no instruction, because it runs very, very fast. So the less instructions you have, the faster your program is going to be as well. It really affects performance, and it's even more dramatic inside inner loops. Anyway, let's end on showing the HASM again. So let's show the optimized assembly for that program. So that would be in the debug folder, test.hasm, and pipe it through more. Pipe, he says, ha. So let's go and have a look at what test method 2 looks like. These methods have gotten pretty skinny. Has it inlined this call? No, call it hasn't inlined it. Oh, I know why. Haha, I'm showing you the wrong thing. I didn't generate, because I'm at the command line, I didn't bother to generate new HASM. So what I should do is do disassemble test, like that. Now it disassembled it. Now we look at more, show it again. And it still hasn't inlined the call. I'm disappointed. But this is what that, oh yeah, this is the two-string thing. Yeah, there's a bit of code out there. Let's do that again and see if we can see where our method is. I'm looking for method 2. So there's method 2. It doesn't enter. Oh, it's at the top of the screen here. So and here's the division and all that. Yeah. So there's no checking. It looks like it dropped the cast. Oh, there's no cast because we didn't do an assignment. Yeah, it just calls into string. It's not that. Yeah, optimization didn't do too much with that. It does pretty well if there's a loop. Anyway, I'm going to end on that. Thank you for watching, and I look forward to your comments. And if I missed something about how the compiler options work that would be useful and interesting, let me know.